Okay, let me recap, right? Again, because I just started the recording. So what did we learn last week in chapter 3? We learned about the design process and the role of CAD in this design process. So what is the design process all about? So we learned, how design should be done very carefully, right? In a very detailed manner. And it should be a very well-organized activity. And we should take into consideration all the influencing factors, right? Which will influence the design to ensure that the product that is designed is successful in its intended use. So it's a very, very careful, detailed process. Okay, and then we spoke about the types of design, and then we contrasted between design in a conventional environment and a computerized environment, hence the role of CAD coming into this. Okay, and then we moved on into speaking about the morphology of design and the phases of design, right, that a product goes through from the conceptual phase right up to the retirement phase. And then we discussed in detail the first 3 phases of the design process, which is the preliminary design process, okay, which is the one you'll be doing for your mini project. And we discussed all the tools that we use in order to justify and evaluate our design, all right? So we had all the multiple tools that we went through, okay? And then we moved on into discussing design for manufacturing and assembly. So what are all the guidelines that's needed for DFMA? So today we move on to, we discussed up to DFA. So today we will move on into design for manufacture, okay? Okay, so design for manufacture, right? So when we design, okay, we should design for assembly, and of course we should design for manufacture as well. So we design for the ease of manufacture of the collection of parts or product. So they say this is more of a philosophy because it's a theoretical concept that we need to take into consideration and put in place so that the entire manufacturing activity is smooth, right, without any defects. So it's a way of thinking that can be applied, to the component of product. And what are the aspects we look at in DFM? So there are many aspects we look at. We look at the operating parameters, operating and non-operating environmental stimuli, so operating parameters in our machine setup, right, for whatever manufacturing processes that we are looking into, be it casting, injection molding, powder metallurgy, right, metal cutting, anything, right? And then operating and non-operating environmental stimuli. So do we have an external stimuli which we need to take care of? Some manufacturing needs to be done in a certain environment. Some needs to be set up in a cold room environment. Some has to be away from heat. So many other things, right? And then what are the testing requirements for our product? The external dimensions that we're looking at for our product, the maintenance and testability provisions of our machinery, right? What are the material requirements, the reliability requirements, external surface treatment once our product has been manufactured, design life of our product, the packaging, as well as the external market, okay? So there are 3 key elements in DFM, design for manufacture, okay? First is the process selection, right? And then, some issues again. Yes, I have same problems again with my pointer, so we'll just go back to the slide, all right? So the first is the process selection. Second is reducing the number of process stages. And third is designing of the process itself, all right? So how do we select which process, manufacturing process? And in that manufacturing process, we want to reduce the number of stages in the process and designing that particular process itself. So let's look at the process selection. So in here, the analysis, this is pertaining to the analysis of material and processing methods for individual components, right? Parts based on the tolerance requirement, the production volume, component complexity requirement, and critical performance criteria, okay? So an example is given here, right? For machining, okay? So what do we look at for machining, all right? We look at machining and we see the tolerance, right? rough machining in inches, plus minus the tolerance of a particular dimension. Standard machining, fine machining, okay, very fine machining, and then grinding, lapping, burnishing, all these things, right? So these are all the processes actually under machining, okay, and the different tolerances that you can actually look at. And based on these tolerances, right, they have also stated the approximate relative cost. So based on the cost that you understand you'll be incurring, and based on the product outcome, we can actually choose the machining process, okay? So, and we also have to look at production volume. So if you want very, very large volumes, then there are certain processes we cannot choose. Like casting is a process which does not generate large volumes. It's more for smaller volumes. Injection molding can be chosen for large volumes. And you can also have very complex, detailed design in injection molding. We can't have that in casting. We can have fine, detailed grooving in machining, for instance. So like that, based on the product that we are designing, we should be choosing the machining criteria. But if you ask me and say, but madam, certain products can only be done through certain machining criteria. If that is the case, then in the step of design itself, you will have to understand there is a limitation. You cannot put in maybe too many fine, intricate details. Like if this is going to be the machining process, like if you have your engine, for instance, it's a casting process, right? So when it's a casting process, then we understand we cannot have very, very fine, intricate design features or profiles. So that is a limitation, and we understand that. And so when we are working on our CAD design, we cannot extend it in that direction, right? So these are all the factors which will help us choose our machining process, right? Next is reducing the process stages. So we want to eliminate unnecessary process stages through component minimization. We don't want to have too many components, right? And we want to eliminate finishing processes in the machining, in the manufacturing process. So certain processes will bring us to some additional process. Like if you do machining, right? Your end product is actually your final, you can reach your final product through the process itself, right? Because machined products usually have smooth surface finish. You don't have to go through grinding, polishing, and all those kind of things, right? But some other products, you need to actually go through those phases. So you may want to see if you can actually select a process which can actually minimize the stages. And sometimes we can combine certain processes together within, like, you know, one-stop machine where we have like lathe machines, they have cutting, drilling, milling, all within a one-stop lathe center. So this one, we can actually combine the processes, okay? So, and we may also want to use easily processed materials, right? We take advantage of materials that have been developed for easy processability. So while the material may cost more, it can often provide lower overall costs, okay? So the example here would be like free machining grades. Many polymer grades are tuned to a particular process, right? Certain type of materials, they actually give a certain type of outcome where you don't need to go on for secondary operations, right? So here we want to minimize secondary operations like deburring, inspection, painting, all right? So it depends on the type of material that we choose, okay? Like pre-painted steel, investment casting, right? Metal injection molding. So these are the processes that can be used to avoid the secondary steps. And then we also want to eliminate unnecessary components so that when we do machining, it is minimized. So this is more of a DFA concept, which is actually brought into the DFM concept, design for assembly. So we learned this last week. You see from 24 parts to 2 parts, right? So here you have to have 8 different parts with multiple manufacturing processes. Here there's only 2 manufacturing processes and only 1 assembly process. So can you imagine the reduction in time, the reduction in cost over here, the reduction in complexity? In every stage there is a reduction, okay? So the outcome of the product must always be questioned. So remember last week we learned about quality function deployment QFD chart, right? The whole idea of a QFD chart is that intended product should maintain that logic flow throughout the process. And then the design of the process itself, we want to ensure the design of the component will satisfy the specific production process. So early on when we said point one was actually designing the process itself, right? All right, process selection. So based on the process selection, we want to make sure that we design in such a way that it fits the process. So if it's for machining, we design for machining. If it's for casting, as I said earlier, we don't want fine finishes. So we should be able to exploit the benefits and the limitations of each of these processes. So these are some decisions, all right? If you have a casting process, you can have this kind of design. If you have a stamping process, then you may have to change your design a little to facilitate this. And both can possibly perform the similar function, okay, these products. So, but the correct decision requires knowledge of the manufacturing process. So you need to understand the knowledge of the manufacturing process in order to actually ensure that the correct design is made. So this is where concurrent engineering is very useful. So as you are designing, the people in the manufacturing department can actually give you feedback and inputs on the troubles you may possibly face when you actually bring your design to the manufacturer. So therefore, they will actually tell you, you may have to cut off this particular design while the design is evolving, right? So this is the idea of concurrent engineering, to mitigate, right, all problems that may occur at the final end stage. So an example, we want robust dimensional fit, right? Design a hood hinge with excellent alignment. So low manufacturing and assembly costs, right? So we don't want a hood hinge. I mean, we are victims of such manufacturing errors all the time, actually, right? Whereby there is no proper fit, and then you cannot fit in, and then all these adjustments become a problem, not only in the hood hinge, but many products where adjustments are needed. Okay. Now, the next consideration, right, other than the DFA and DFM, would be these three factors, right? The product use, design life, and human factor consideration. So for the product use itself, just give me a minute there. We'll be back. Okay, sorry. Yeah. Okay, so now we come to the other part of it, right? So what are the other considerations? Now, product use. So this goes by the tagline that the customer is always right. Now, is this to be taken literally? Not like that. Not that the customer is always right in the sense that we have the theoretical knowledge, right, correctly. But how is the customer always right? The customer is always right in the sense that they want a product which is comfortable for use. They want a product which is efficient. They want a product which has been promised to them, right? So if you claim that your car can do this and that, and you state 10 functions in the product design specifications or the product specification, then the customer has the right to expect that to take place. So that's how we say that the customer is always right in that sense, okay? So, and when the customer comes back and tells you, hey, you promised me 10 functions, right, in this product, but somehow or other function 5 and function 6 is failing. It's not meeting the requirement as stated. So we do not tell the customer, oh, it's in your mind, it's in your head, I think it's in your discretion, or you must have used it wrongly. Instead, we should investigate their claims. Okay, please bring your product over. So that's what customer feedback is all about. That's what service centers are all about, right? Post product service is all about, whereby when we come back, they're supposed to troubleshoot, and if at all the customer got it wrong, then it's the duty of the manufacturer or the marketing team in the sense, or the service team in the sense, to inform the customer, okay, this is how it should be used, this is how it should be done. So this is basically like the concept we go about in the sense when we say the customer is always right. Okay, so in the US, consumer products are developed under philosophy, all right, under this philosophy, and whereby there are many things that customers usually go for. It's just a common thing, right? In customers, we want to pay the least, but we want the best in quality. So now, this is not always possible, but we need to actually strike a balance between quality as well as cost, right? So in the case of engineering products, right, we have many types of products, right? If you want sophisticated products, you want products for long-term use, then we understand, like you don't buy a car for 5 ringgit, you buy a car for thousands of ringgits, right? Or hundreds and thousands of ringgits. Why? Because its lastability is supposed to be, its product life duration is supposed to be a prolonged one, right? Minimum 5 years use, 10 years use. Like many cars actually now in the market give you 5-year warranty for many of their parts and sections, okay? So kind of things are definitely not going to cost, not going to have low cost. Otherwise, and now on the other hand, if you look at simple products, like, we buy, in our, let's just say, like shops, like, DIY, Daiso and everything, there we pay very minimal price. And the understanding is, once you use, in its, let's say, usage period, it will be very small. And once used, it's usually not reused again, it's discarded. So hence the price is low. And there will be a quality compromise over there. So this is understood, right? So it's up to the customer to actually make that decision when they go about purchasing any particular product. So when we look over here, customer, they will demand, right? Normally demand for performance, reliability, serviceability, reasonable cost, safe operation, and a good human engineering ergonomics, right? Customers' expectations are compared with various product design characteristics to identify those that are not addressed and to develop an optimized product plan incorporating design, modifications, and accommodating the dominant expectations. So how do manufacturers go about taking the feedback from the customers is they collect all feedbacks, but they will, categorize the dominant expectations. And in that dominant expectation category, they will ensure that it's, of course, feasible to serve the customer. All right. So if it's not, then there will be feedbacks actually raised and given back. So product liability in the US, right? It's a design consideration that's of growing importance, right? Users of products are increasingly aware of their opportunities to sue the manufacturers, and court sentiment often leans towards the customer even when the product misuse is involved. So you can see over here, right? In the West, this is quite prevalent actually, where very easily you can actually bring the manufacturer to court, right? You can sue them for their lack of performance or lack of delivery in their product. Like even in Europe, right? Let's just say clothes and everything. They have concepts where you can actually purchase them, you can use them and return them, right? Within a certain period of time without reasoning, right? Not that you have to show that it's torn or this or that, but it's because you just dismiss, you don't like it. So you can imagine when such sentiments are there, what kind of strain the manufacturer will be in to actually design a particular product. They will take their job of designing seriously. They will take their job of manufacturing seriously. When the competition is high, when they know that customers are aware of their rights, right, then they will ensure that the product that actually meets the market, is being sent to the market, will meet the customer's demands as best as it can, right? This is one thing the manufacturer, we engineers, need to consider when we are actually designing a particular product. Now, the next thing is the design life itself. So this is linked to the first point itself, right? When you're designing something, of course, the nature of the quality and the cost is dependent on the design life. And after that, they have to also ensure, see, many engineering design products are designed for a specific installation or assembly, and it's normally assumed that they will remain in this application for their useful life, right? So design life in terms of cycles or hours of operation, we should design, right, in terms of cycle or hours of operation, and it's a fairly straightforward task to design, okay, and test the product to meet these requirements. So while we're looking at the design life itself, right, the investment in the design and the usage of the product also determines the cost. Next, we must give consideration to the retirement of the product, all right? How long does it take for the product to be phased off the market? And also how the product is going to be phased off the market. So we have many, many products which are not phased off properly, which creates environmental effect and impact, right? So while this product proved to be, very outstanding, like we have our electric cars and all those things, but how are we actually, recycling the batteries? How are we actually recycling the entire concept? Not recycling the concept, recycling the products, okay, for the new conceptual designs that we are actually proposing. So all these things need to be looked at seriously, right? So there is no point designing something to solve one particular problem if you are going to bring about larger problems in the long run of the usage of the particular product, which is why we say when we design something, the first few stages of design, it's a very difficult one because it's contemplating multiple consequences of the design. And then the third one is human factor consideration. So we've gone through this before. We always look into the ergonomics of that particular product. So the ergonomics aspect is looked at not only from the user endpoint, but also the operator endpoint. So a person who's actually building the product, okay, also needs to be comfortable in the particular building, right? So if you're making a car, so those operators in the assembly plant, right, should be having an environment where when they are doing their assembly or manufacturing and everything, they are not stressed in the physical point of view or safety point of view when they are actually manufacturing that product. As a user, when you are using that product, you should not have any discomfort and it should be safe. So it should not create any physical discomfort. So here we look at a significant amount of anthropomorphic information, right, to determine like the size of the population. So anthropomorphic information means the population sizes, right, to see how we design products to suit different population. So an individual's capacity for doing work should be considered in the design. For repetitive tasks, a system layout should be selected that minimizes boredom but does not involve overload in the individual capacity, right, to comprehend. This is from the operator point of view. From the user end, the product must be aesthetically appealing because many products are purchased primarily due to their looks and maybe the feature that initially interests the potential buyer. So this is, in my personal opinion, quite a sad phenomenon because everyone goes for the aesthetics first. Sometimes people don't even look at the functionality and the safety description of the product, right? So hence, a lot of stress is given on the aesthetics, the appeal of the product. So as design engineers, we know that this is a factor that is sought after. So we need to keep this in mind when we are designing. All right. So this ends the first part of chapter 3, and now we'll look at the second part. Okay. So the second part is actually speaking about the aspects of concepts of manufacturing. So we will go through this a little quicker because this is more of an information, right? This generally does not come out in your test much. And to understand this in depth, you should be having more of a hands-on experience, right? So when we look at computer applications, there are 3 major areas, right, where computer applications are important. It's in the design, analysis, and manufacturing, major areas, okay? So the computer application in design, right, what do we have? Application means software, right? So the computer application in design is, right, we use this to actually build our geometrical model. Basically, in design, what are we doing? We are actually building our geometrical model. The software is to actually build the geometrical model. And then for the design itself, that is the main purpose. So it uses both hardware and software, and it's for the purpose of visualizing and styling the product. So this is what is there, right? Widely, the wide usage of the CAD tools. We need graphics and we need 3D modeling capability in order to actually build the visual design. So what are the hardwares that is needed in design to ensure our software runs? We need like scanners, 3D scanners, digitizers, pointing devices, our mouse, and everything that is needed to actually build the design. Softwares, we have like AutoCAD, Pro Engineer, SolidWorks, Unit Graphics, Catia, and many more actually. You know, it's a whole load of software in the market right now, okay? What about computer application and analysis? So after designing, we actually analyze and optimize and verify our product, okay? So the tools, right, used are like finite element analysis, computational fluid dynamics, ergonomics, and everything, whereby they use the formulations, all right, this, all right, to run the analysis to study the strength of the structure, right, heat transfer, the nature of the fluid flow, etc. Okay. What are the types of softwares? We have like Abacus, ANSYS, Mannequin, even Catia has its analysis package, okay, and many more. Computer application in manufacturing. It's mainly used for planning, monitoring, controlling, and executing the manufacturing process. So we also study the manufacturing process itself, right, through the computer software. Like we try to simulate the injection molding process, we try to simulate the casting process. Once that is done, then we also manipulate and operate our entire manufacturing setup through computer applications. So the tools are like computer numerical control machines, right? And the softwares are like Mastercam, Moldflow, and many others that come about, okay? iCam, we have. Even Catia has its manufacturing unit, right? We can do simulation for lathe, machine, yeah, lathe and basically machining for cutting and lathe machine. I think Catia has it, right? Okay. Now we move on into what is called the digital mockup unit, DMU. So what is this? The digital mockup unit is actually a concept that allows the description of a product, usually in 3D. But we're talking about a product, that means assembly of multiple parts. So it comprises of 3D models which are positioned in space to 3D space to represent the form of a product to be developed. Basically, they're saying that we can get the entire assembly of the product and display it in our monitor, and we can actually study the entire nature of the product. So the objective is to have an important knowledge of the future or the supported product to replace any physical prototypes. So when we can actually view our full assembly, we do not need to have the physical prototype. What are the roles? To allow full visualization of complete product in 3D. It permits collaborative engineering as all users can see other users' work as the product evolves, and it improves error detection by locating clashes and interference in the manufacturing process, basically by viewing the assembly of the product. So the goal will be obviously to reduce the time to market by identifying potential issues early in the design stage or process stage, reduce product development costs by minimizing the number of physical prototypes that needs to be built, increase product quality by allowing a greater number of design alternatives, right, to be investigated. So this is self-explanatory. So now here, okay, it's a video of DMU kinematics.
Hi, this is Mohammed Shakil here, and you're watching an engine being designed in the Power Design Workbench, and a little bit of combination of generator shape design, and it's being brought to the DMU Kinematics Workbench for a simulation. So basically, I'll show you how the simulation works. So reduce the velocity, and so as you can see over here, you have the basement here, and a wheel here, and a piston.
Oh, sorry, wait.
Hi, this is Mohammed Shakil here, and you're watching this workbench for us. And
Okay, so you can actually see now the
so
movement.
as you can
You can actually see the movement of this product, right? It's motion of mechanism within an assembly.
see over here, you have the basement here, and a wheel.
So here you can identify, right, the potential clash, the interference, or anything. So you actually can view how your product will really function in real life.
Here, and
So this is done
a
through the
piston,
assembly
and
module. So
what
I'm just going
happens here,
forward
motion over here is
and
being
simulate the
converted to
motion
the
of
rotary
mechanism.
motion
So
of
this
the
is a
wheel.
display of simulation.
You can create your own simulation. So basically, it has to follow certain rules as well.
Okay, all right. So you can go through the full video if you want to. Okay, now we move on into computer-aided process planning. So what is computer-aided process planning? So this is the last part of, okay, this is the last part of this chapter. So what is computer-aided process planning? We would have seen this terminology in chapter 1 when we described, all right, all the different abbreviations that we use in CAD. So basically, it's an ability to plan the process of manufacturing with the aid of computers. So we saw that in the, when we contrasted the conventional manufacturing and computerized manufacturing. So in the computerized manufacturing, you would have seen that we have computer-aided process planning, where the entire manufacturing process is planned with the aid of computer in different departments. So the process planning begins with an examination of an engineering part, drawing, okay, the detailed drawing, and ends with manufacturing process plans and instructions. So what are this? Act of preparing process documentation for the manufacturing of a piece, part, or assembly, right? So you have your CAD model, which ends up in your engineering drawing. And from that engineering drawing, you plan your entire procedure of manufacturing, right? Which brings about your final part. So in this, we have two levels. We have the high and low level planning. So the high level planning is a general planning, okay, which identifies what kind of group is going to do this, what the personnel is involved, which project team is in it, right? And all those things. The lower level planning is the detailing of that above high level planning, whereby you have a smaller group who's going to actually get to the process, get to the work, all right? And how do we get into that work? Actually, that small group will be the one actually ordering the material, coding the NC code for the machines, and then running the machining, all right? So process planners follow a consistent set of steps, the standard operating procedures. Yeah, like your lab sheets. If you all walk into your labs and say, okay, we run this experiment, so you're like a process planner. So you're not a process planner, you're the process executor, all right? So the process planning has been done by either your lab technicians or your lecturers or whatever, and they've given you like a root sheet, not a root sheet, lab sheet, right? So this lab sheet will tell you the routes in the process. So it usually involves primary stock preparation, plan generation, and specification of manufacturing procedures. So traditionally, process planning is performed manually by highly experienced planners who possess in-depth knowledge of the manufacturing processes involved, and the capabilities of the shop floor activities. So shop floor is the production floor, all right? So how do you do process plan? Cannot bring you and me and simply walk into, let's say, any manufacturing plant and say, okay, let's plan. We won't know the machines. We won't know the capability of the machine. We won't know the capacity of the machine. We won't even know what is the flow of the production. So who knows this? These are the people who are there on the shop floor, in the production floor, who've been doing this repetitively. So development of a new process plan is highly subjective, labor intensive, time consuming, tedious, and often boring. Okay, when you want to actually come up with the very first process plan. So definitely a lot of involvement is there. But once that is set up and you're going to run your repetitive manufacturing, then it becomes just a routine cycle. So computer-aided process planning is a means to automatically develop the process plan from geometric image of the component, where it integrates CAD and CAM. It takes the CAD data to the production data and feeds it into the production system. So how does this happen? How does this happen? All right. You have your CAD, right? Your model. You see this in your Catia right now. The model is saved, and then when you actually bring it into your manufacturing software, like any Mastercam or anything that you're going to use, right? Let's say you're doing injection molding, you're generating the machining. So if you're doing your machining, right? So you will see the machining simulation. If everything goes well and fine, you can actually click generate the NC codes. So it will actually give you. So your model is there, your analysis is done, your manufacturing simulation is done, and then now you actually generate the cutting codes, the NC codes, and you just have to send it into your manufacturing machine. So if you notice, there is no really, as per se, a lab sheet or a root sheet or a standard operating procedure, because it's very much dependent on your CAD model. All right. So this is the computerized environment. Now, in a conventional environment, it won't work like this. What is a conventional environment? For you all to understand what a conventional environment is when you all walk into your individual labs right now, manufacturing process lab or any other labs that you've been to. That's a conventional environment. Where you walk in, you have a lab sheet, and then it follows a standard operating procedure, and it's been done before, and then someone brings you, and then you run the experiment. So that's a conventional environment, okay? Now, key to develop such CAD systems, what do you need? Of course, we need the part design, so we need a CAD model. You need the manufacturing capabilities. You cannot have, you need the manufacturing facility, right? So you need a facility where you need machineries which can actually bring in this numerical codes and everything and link between a CAD and a CAM system. And you need manufacturing capabilities. Even if you have the machine, as I said, the machine should have the capacity to be able to do that. So these are basic steps of process planning, which I will not, we can just run through this. Basically, you need to have your part requirement, you need to get your raw material, determine your manufacturing operation, tools, what are the jigs and fixtures, what are the machine conditions as in the cutting. So this is a full set of manufacturing knowledge which you need to have for the different manufacturing machines that you're going to use, okay? It's an injection molding machine. You need to know the standards for the injection molding machines. You need to know the operation, the procedure. Machining, different. Casting, different. So what are the benefits of computer-aided process planning? So it reduces process planning effort, right? Systematically produces accurate and consistent process plans because you're linking directly to your CAD model. So this saves direct labor. We don't need too many people because it's computerized. It saves material because, of course, we have already checked all the error prior to that. So saves scrap. It also saves your tools because we already know the nature of your manufacturing and how your tools will behave in the cutting. So we can actually forecast where your tool failure will take place. It reduces the work in progress. So while the work is in progress, right, in a conventional environment, it is a prolonged manufacturing line, whereas in a computerized environment, it relies fully on the computational message passing, right? And then it reduces process planning lead time and there's greater process consistency. So when we look at the CAD model, so what is there in a CAD model? We have our CAD system. And then in our CAD system, we have our CAD model, right? Whatever you're doing. And then we have our preprocessor. So from the preprocessor, what happens is the CAD model is such, the model, your geometric model, is sent in as an input to your CAD model, okay? So what is this CAD model? Basically, it is literally just a model which helps you collect the manufacturing information to generate your product. So inside that CAD model, what do you need? You need the knowledge and the planning rules to get your output, right? To plan your production. So this is the CAD system and this is the preprocessor. What is the preprocessor of your CAD system? In your CAD itself, you already define your material, you define your geometry, you define everything. So when you come into your manufacturing, right, environment, what do you need to do? You see, knowledge and planning rules. So what is the knowledge? Your machining knowledge. So how do you know what your machining knowledge is? You need to get it from your machining knowledge base, usually from your machining manuals. If you have a manual, it will tell you how to actually go about doing it. It will also give you your limitations, right? And capabilities. And then you also have, planning rules, all right? You have your constraints for that particular machining setup. So, you know, you can only use this with a certain temperature, only with a certain material. So all these constraints also come from your machining, not from the machining knowledge base. This is more of the, not the manufacturing knowledge base, more of the machine specific information. So pulling in the constraints from the machine and from your manufacturing knowledge base, you will get your process plan generation. So there are two approaches to CAD, which I mentioned just now, right? We have the conventional method, like how you all are doing when you go into your lab, you do your lab sheets, you do your lab experiment, which generally uses what we call the variant approach, and the generative approach, which I said that you directly links CAD to CAM. And then we have a combination of both, which is called the hybrid approach. So what is the variant approach? So the variant approach is also what we call the retrieval approach, right? What it does is it uses a group. This is specific to manufacturing environment. So if you tell me like, oh, madam, when we go into our lab, we don't need to know the codes, the group technology, etc. Everything. Yes, true. Okay. I'm just trying to give you an idea of how a variant approach will be because it's rather conventional, right? But in the actual manufacturing setup, all right, the lab technicians actually know the specific codes you need to press in order to run the machine, okay? So what they do is they use something called a GT, a group technology code, to select generic process plans from the existing master plans, right? So the first setup of an experiment, if let's say I create a new subject, right? And now I actually need to set up the machining, the lab sheet for it. So I have to come up with the experimental step. So the first setup is naturally going to be tiring. It is a lot of time consumed. It's very time consuming, right? And it's a very detailed process. I have to make sure that, you know, every step is correct. So I must have experimented it out, test run, then only I have to give you all the actual test steps, right? But once that is done, and then we start following that cycle step, right? Even if your product changes, the steps will be pretty much the same. So this is where they say about 90% of the baseline process will be the same. Okay. Your lab sheets now, right? Let's just say you're going to do injection molding. So, okay, so these are all the standard procedures. Now, let's say I want to mold another part. What happens? You need to change the mold and generally run through the standard procedures again. Okay. So this is commonly implemented with group technology coding, right? This is basically under the machining, right, part. Parts are segmented into groups based on similarity. So when you are doing mass manufacturing, naturally we will classify the same types of part to be manufactured so that we minimize changes in the machining parameters. So there's a challenge, obviously, to develop the initial GT codes, but once developed, then you can just use the same GT codes. So this variant approach is impractical in situations where small batches of widely varying products are produced. So you imagine that, you know, you keep changing a product completely, right? Keep overhauling it, then it becomes a bit of a annoyance, a complication. Now, what's the disadvantage? The quality of the process plan depends on the knowledge and the background of the process planner. So assuming I have understood the machine wrongly and have made some assumptions wrongly, then you will actually get an error in your output. So there's a possibility of repeating mistakes from the earlier plans. Now, the advantage is good investment where the hardware and software required for the CAP is not so high because it's more conventional based, and often shorter development time and lower manpower to produce the process plan. Now, implementing a variant CAP system is straightforward since it uses the existing process plans which are already required. So a variant system is a very direct, straightforward thing where you have a machine, you have a product, you have an idea of manufacturing it, you have to come up with the lab setup, the experimental setup, or the manufacturing process setup and run it. And that setup, in the case of manufacturing, we will have certain codings. Now, what do these codings represent? Like we call this group technology coding, right? So just one example that we share with you. This is not, this is an added information actually. All right, they have 3 basic codings, but the one of it is the chain type structure called the polycode. So what they will tell you is now, how do you code when you bring your product and you go and give it to the lab technician? There will be a code. The lab technician will read the code. How the code will look like. The first one, right, describes material. The second one describes material form. Third one describes material property. Fourth one describes the bending method of the process. Fifth one describes tolerance, surface finish. So like that, there will be a coded value depending on the digit or the alphabet, right? Material M1, so it could be steel of this. Material form, right? Whether it's in sheets, whether it's in billets, whatsoever. Material property, okay? What kind of bending method? Okay, let's say there are 5 types, then there'll be bend 1, bend 2, bend 3. So like that, I'm just giving you examples, right? So as soon as the technician reads the code, or the person who's actually handling the machine reads the code, they will just, it's like matching your procedure and running your machine, okay? So these are like examples of process sheets, okay, given, okay. And so this is how the group variant approach happens, right? You have your CAD drawing, it goes into group technology code. And then you're from your CAD drawing, you actually develop the code, okay? And then you get your process plan and you embark on your manufacturing. Once your manufacturing is done, this process plan is sent back to your master plan for storage so that you'll get a library of process plans, which you can later retrieve and use back for future experiments. Now, what is a generative approach? It's a process plan created from scratch for each component without human involvement, where you're looking at directly from the CAD model, it goes into your CAM, and from your CAM, straight into your manufacturing. It does require a predefined master plan, as in you have to understand the nature of how the machining takes place, but most of the time it uses computer logics to actually link, all right? How it does is it uses process plans, which generates decision logics, formulas, algorithm from decision logic and formulas, okay, technology, algorithm, and geometry-based data. Sorry, excuse me again, a little while. Okay. All right. So now implementing this generative approach, okay, requires a little bit more effort than the variant approach because it's not conventional, it's more computerized. So when you actually have a computerized system, the technicality and the complications are higher in the initial setup, the build up, right? But once that is the established system, then it becomes easy to follow up, right? So the advantage, fully automatic and up-to-date process plan is generated each time a part is ordered. Disadvantage, it requires major revision and decision logic if a new equipment is brought in. So you have a full overhaul of it. So what is the generative system? You have your CAD model over here, right? And then you have your process plan logic. And then you get your final process plan. Now, how is your process plan logic developed, right? From the manufacturing facility information, right? And when they mean this, they mean your CAM system, where you have already tested your machine tool, your cutting tool, and all your entire environment and setup is already pre-simulated. So that's where you get your process plan logic. So the CAP implementation techniques, they use 3 types: the decision table, decision tree, and AI expert systems. Okay. So under the decision table, so you have, I'll skip the write up and go straight to the table itself. All right. So basically what this does over here is, assuming you're just specifically zooming into a particular manufacturing scope. Okay. So let's say you're doing cutting, all right, on a machine, and we'll have many conditions, but if you're looking at 2 conditions here specifically in one environment, where you're going to actually do cutting, where during the cutting, it describes, let's say, condition 1 is the lubrication and condition 2 is the speed. So let's just say if the speed is low, the lubrication is of a certain dose, what is dosage? A certain volume, right? So if the speed is higher, then the lubrication is of a certain, or should be on, should be not on. Okay. So let's just say you have condition 1, which is lubrication, and condition 2, which is speed. So based on high speed, you need to on your lubrication. Based on low speed, let me give you a better example, right? Let's say condition 1 is lubrication, condition 2 is okay. Condition 2 is lubrication, condition 1 is, let's say, cutting speed. So let's say based on your cutting speed, you need to switch on your lubrication, you will say yes, yes, all right? Referring to a different cutting speed, if you do not need your lubrication, then you will say no, all right? If there is no movement in your tool, as in no cutting speed, should you be on your lubrication? You may want to, just to cool the environment, then there is a yes. There is no cutting, no lubrication at all, then no. So you understand a mismatch: switch on of a machine, switch on of lubrication, switch off a machine, switch on of lubrication for cooling. So like that, basically what you do this in programming. You give if and or, so this kind of setups, all right? So we will decide the type of actions, and then based on this, we will actually program and key it into our machining setup. So it will automatically detect and it will run the sequence. So you use something called the decision table, which can be actually converted into a decision tree. So what's the difference between both is just the presentation method. Okay. So if ever any test questions have come out before this from this part, is actually this one here, where they actually give you a decision tree and ask you to convert to a decision table, or vice versa. Okay, so this is pretty. The other aspect of it is AI, artificial intelligence. So what is with the artificial intelligence? Basically, it's using artificial intelligence to actually sense our machining system. So we know our machines are robots, right? And they go based on the codes they are programmed to do. Actually, basically the machines run based on the programming that has been programmed. Now, how do you enhance the functions of the machine? We can actually use AI. So how is AI exactly used? It actually incorporates a lot of sensory mechanism. For instance, if you have a pick and place robotic arm, which is now picking and placing products which is coming out of a conveyor belt of the manufacturing, and maybe the products that come out have a certain heat, right? So how does the robotic arm actually pick? Does it pick everything up? No, there's a detection heat sensor maybe at the bottom. So if the heat is not correct and it needs to run through a round of cooling, it will sense the heat, it will let it go. If the heat is correct, it will pick and place. So like that, it looks like that particular robotic arm has its own intelligence, but basically it's not the intelligence. It's incorporating extra sensory devices to present it as a mechanism having an own intelligence, right? So that's why we call it artificial intelligence, right? So the more the sensory devices incorporated within robots and machineries, the better you actually improve your manufacturing processes. Okay, so this is like a summary of how a variant approach will be. You have your CAD drawing. Once you code it, right, you get your process plan, and then you store your process plan in your library, right, once your manufacturing process is done. In the generative approach, you have your CAD drawing, you have your interface engine. What is your inference engine? What's your inference engine over here? The interface is your CAM, where you can run your entire simulation process with different cutting speed, injection speed, everything can be checked based on your machining or manufacturing knowledge. And then you get the final plan, and that is the thing that is straight away incorporated. So there is no standard operating procedure in that sense, okay, because it is custom made to your product. And then we have the hybrid approach, which actually mixes both up, right? Okay, the last few slides over here just actually describes the manufacturing environment. So in a manufacturing system, right, a CAP system, we actually need the part design representation, we need the manufacturing resource representation, and we need the process plan representation for the entire CAP system to run. So what is computer integrated manufacturing? I've actually added some video which you all can actually look through, right, in your own time. So what is SIM all about? Is it only the integration of CAD and CAM? No. It is actually the integration of total manufacturing enterprise through use of integrated systems and data communications coupled with new managerial philosophies, which improves the organizational and personal efficiency. So basically, incorporation of CAD and CAM with managerial philosophies, like I've mentioned earlier, we have, just in time, Kaizen, Kanban, Six Sigma. So what are all these managerial philosophies? It's philosophies which actually are used to improvise your product presentation, product delivery, product manufacturing, and all these things, right? So that is a complete integration. So it basically involves the function of the entire enterprise. Go to this slide first, right? Whereby the success of an enterprise depends on the customer. That concept has to be there. Otherwise, if you bulldoze into the customer, your society, without taking into consideration their feedbacks, you're not going to be able to improve your product. It deals with the organizational structure of the enterprise. So the organizational structure should be clearly defined. Who's the head? Who's the project leader? Who's the team leader? Who is the shop floor technician, all those things. The shared knowledge should be present, where it should be concurrent. Anybody from any department has access to the evolution of the product, both the database and the experience. All the systems in that enterprise should be involved in the manufacturing of the product, and the resources and responsibilities of the enterprise should be taken up by each and every individual serving the enterprise, all right? So it's not like, okay, I'm working in Proton, so only the CEO needs to be bothered what happens to the machine. I don't care because I'm just an employer. No, that's not the case. That ownership and right should be there at every phase, every department there is. Then there will be success in that enterprise. And we must have the state-of-art manufacturing infrastructure. So when we say state-of-art, current manufacturing systems, machines, capability, only then you can be competitive in the current world. So you can see over here, right? The customer is the center, and then we have the people, the teamwork, and the organization, and then shared knowledge and systems. Then there should be customer support, product process, manufacturing, etc. Okay, this few slides are just added information, so it's not really part of your test, right? This just tells us the interaction of the tooling system with other functions in CIM. CIM, Computer Integrated Manufacturing, how the tools are needed to ensure that the CAM and the productivity activity actually runs. The implementation of computer integrated manufacturing, starting from the equipment, moving to the workstation, to the cell, to the system, and finally to the factory. Okay, how it works. The major functions in computer integrated manufacturing, where you have your design and engineering, your master planning, your sales and order, your process planning, quality assurance, and some interface requirement whereby your process and operations planning, when you're talking about a product, we have service industry and product industry. So when you talk about the product industry, then we need all these functions running. Okay. Finally, the last slide. What is the benefit of computer integrated manufacturing? It improves operational control. So when your operational control is improved, then your product control improves. Your product outcome improves, right? It improves short-run responsiveness consisting of engineering changes, right? When you have any type of engineering changes, product changes, process changes, including machine downtime. If your machine breaks down, does everyone go into a complete stop? No. If you have SIM and you have pre-planned all these things, you should be able to kickstart with another machine. Alternatives should be there. Operator unavailability, cutting tool failure, late material delivery. So all these things are improved because these things are forecasted in a production process, whereby we will forecast an operator falling sick. We will forecast a machine downtime. We will forecast the material will come in late. So I should have some storage material like that. It improves long-run accommodation through quicker and easier assimilation of changing of new product volumes, new product additions, and different part mixes, right? It reduces inventory and increases machine utilization. All right. So this is the end of chapter 3. Are there any questions from you all? Any questions from anyone? If no questions, okay, so we are done with chapter 1 and chapter 3. Okay, so next week will be a Raya break. And after that, Dr. Helmi will take over for chapter 2 and chapter 4. All right. So the link will be sent by Dr. Helmi, and then the respective lecturers will share it with their classes. Okay, then. So thank you very much.